Welcome back to Calculus 1. I'm Dr. Jeff Crow. Today, we're going to introduce one of the most important topics of the entire calculus sequence called the derivative. You may be surprised at how many applications this particular concept has. The derivative models rates of change. If something changes, it's likely going to be modeled using a derivative. Though the origin of the derivative is humble enough. Suppose we have some function, and we would like to find the slope of the tangent line. The tangent line just grazes and rests on the surface at one point, let's say at A. So what is the slope of the tangent line? The problem there being that the slope formula from algebra involves 2 points. You have to have 2 points, x1, y1, and x2, y2. Then you find the change in the y's divided by the change in the x's. So how do we find the slope of this line if we only have this one point, a, f of a? What we'll do is we'll use 2 points. We'll back away from this point A to some point A plus a little bit, A plus H. That will give us a second point to work with on the graph. We'll construct what is called a secant line. A secant line passes through 2 points on a graph, and that's what the secant line means. So, how do we then calculate the slope of the secant line? Note that we have denoted this little gap by h. Though it is a difference between these two x values, sometimes it is called delta x as well. This gives us 2 possible ways of writing the slope of the secant line. The y values plop out of the function f. And so we'll have f of a plus h minus f of a as the change in the y values. The change in the x values is either h or delta x. So another way of writing the same thing is f of a plus delta x minus f of a all over delta x. We'll see both of these. Now, the bigger you make this value h, the worse the approximation to the tangent line is. You do better by making that gap smaller. In fact, we would like to take the limit as h goes to 0. It stands to reason that that should give us exactly the slope of the tangent line. That's right. The slope of the tangent line should be exactly the limit as h goes to 0 of f of a plus h minus f of a divided by h. We can do this at each a on the domain of the graph, provided the limit exists. We'll make the following definition. The derivative of f at x is denoted by have to be honest with you, there are several different notations for the derivative. So I should give you a few of them. First, we can often denote the derivative by f prime of x. If we have a function y equals f of x, we sometimes denote the derivative by y prime or dy dx. The reason why you have dy dx is we sometimes think of dx as an infinitesimal change in x, and dy is the resulting infinitesimal change in y that results. In the limit, of course, as that little change in x goes to 0, you get exactly the ratio dy over dx instead of delta y over delta x. This notation dy over dx is due to Leibniz. Leibniz invented calculus independently of Sir Isaac Newton. Newton's notation for the derivative with respect to a spatial variable was prime. So here we have, at the very earliest moments in the development of calculus, this notation that was introduced by the two competitors who claimed to both independently invent calculus, Leibniz about 10 years after Newton. Another notation might be dx of f. Sometimes you'll see a capital D as a derivative operator being applied to a function which outputs the slope of the tangent line. And defined by, I'll write it as f prime of x equals, because I said so, the limit as h goes to 0 of f of x plus h minus f of x all over h. I want you to inscribe this notion on your brain and never forget it from this moment forward. Let's calculate one of these just to get some practice with what we're doing here. Let's find the slope of the tangent line to the function f of x equals x squared at a equals 1. This should be the derivative evaluated at 1, and that should be the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. F of 1 is 1 squared, or 1. So we'll begin the next line with equals, and then limit as h goes to 0. Don't forget my equals. Don't forget my limit. When we evaluate the function at 1 plus h, we'll have 1 plus h quantity squared. Students often get confused about function notation. That's why we spent so much time in the last module talking about this notation. Minus 1 all over h. As you can see, if you just plug h equals 0 in now, you'll get 1 minus 1, which is 0, divided by 0. What does that mean in the context of limits? More work. So, let's FOIL things out and see what happens. We'll get the limit as h goes to 0 of 1 plus 2h plus h squared minus 1 over h. Now don't be forgetting my middle term. As you know, if you have a plus b squared, I want you to think about that. This is something that students at this level screw up all the time. You have to FOIL this, which is an acronym for first, outer, inner, last. If you multiply the firsts, you get a squared. If you multiply the outers, you get AB. If you multiply the inners, you get BA. And if you multiply the lasts, you get B squared, which is A squared plus 2AB plus B squared. You get this middle term. Don't forget that middle term. In this case, first times last times 2 is 2h. As you can see, the ones cancel. Now we're left with two terms in the numerator. Terms are separated by plus or minus. Factors are separated by times. We have two terms in the numerator, both of which have a common factor of h. I'll factor the h out. You can see now that one factor of h cancels from both the numerator and the denominator. You may cancel common factors in a fraction, not terms. You may not cancel from terms. So now, all that's left is 2 plus h, and h is being sent to 0. The limit is 2, and that is the slope of the tangent line of this function. This function is a parabola, and at x equals 1, the slope of the tangent line is 2. I should point out that unless you can cancel that h in the denominator, you screwed up. Before moving on, I'd like to give you an example that I hope will help illustrate why this concept of the derivative is so important in physics. Let's suppose that this is California. We have Nevada over here, and there's Oregon, and Washington State, and then there's Idaho. Suppose I'm going to drive from Fresno, California, where I was born and raised, and go up to Sacramento and cross over at Donner Pass, go to Reno, up to Winnemucca, over to Elko, up, and then over to Pocatello, Idaho, down in the southeast corner of Idaho. It's a travel of about 1,000 miles. Now, I've made this trip on more than one occasion. Sometimes it took me 15.5 hours, sometimes 17.5 hours, depending upon road conditions. Let's suppose I did this 1,000 miles in 15.5 hours. How fast was I going? There's an old formula that you are familiar with. Distance equals rate times time, which means then that rate is distance divided by time. Miles per hour. So we can calculate this as 1,000 miles per 15.5 hours. Well, how much is that? My calculator tells me it's about 65, and I'm putting a dot over the equal sign. Whenever I put a dot over the equal sign, that tells you something specific. I'm trying to convey to you that I'm rounding the answer to some decimal place accuracy. In this case, to the nearest units. This says something slightly different than approximately equal to. 67 is approximately equal to 65, but it's not rounded to the nearest decimal point. When I put the dot over the equal sign, it means I'm rounding to whatever decimal place accuracy that I'm giving my answer to. Now I want you to think about this 65 mile per hour answer that we have. I was driving a 1978 Ford Fiesta, and it could not go 1,000 miles without refilling. In fact, its maximum range was about 280 miles. So it's a fair bet that I would have to stop for gas 2 or 3 times along this journey, 3 or 4 times perhaps. At those times when I was stopping for gas, I was going 0 miles per hour for a stretch of maybe 10 to 15 minutes. This number, 65, doesn't really tell you how fast I was going between Elko and Winnemucca. After all, what is there between Elko, Nevada and Winnemucca, Nevada? The answer to that is basically nothing. In truth, I was likely going 85 miles per hour between Elko and Winnemucca. So you can see this 65 doesn't tell the whole story. What is this 65 number anyway? The 65 mile per hour number is not the speed at which I was typically traveling down the freeway. It's the average speed, including the dead stops. How can I get a better estimate for how fast I was going at any particular moment? And the answer to that is, I need to take these estimates for the average velocity over smaller and smaller time intervals. Let S of t be the distance traveled at time t. So for instance, at t equals 0, I might have traveled 0 miles down the road. At t equals 15.5 hours, I will have traveled 1,000 miles down the road. So this is how far I've traveled after t units of time. You can see then that the velocity at time t can be evaluated in the following way. First of all, I'll have to take a limit as h, the time gap, goes to 0. What I'll do is I'll take the position at time t plus h and subtract the position at time t divided by h units of time that have elapsed. The difference between t plus h and t is h. This is the change in time. We can think of this velocity as the limit as delta t goes to 0 of the change in position divided by the change in time. Distance divided by time is rate. But we have to take the limit. Now, Newton would not have used a prime in this instance, because whenever he took the derivative with respect to time, he denoted that derivative by a dot. You should know this notation. We've seen now that the physical concept of velocity is the instantaneous rate of change of distance with respect to time. Whenever I introduce a new concept, I like to, first of all, make sure that you remember the precise meaning of the words that I'm introducing, and also, I like to proceduralize it. I like to show how you functionally implement that definition. The ability to functionally use a concept and the ability to remember the concept are two separate things. Let me give you an example. In the literature, there's a woman known as LP. LP had encephalitis, which is a form of inflammation in the brain. and as a consequence, she had permanent damage to her lateral temporal lobes. She retained the ability to multiply three-digit numbers and carry out exponents, but she lost the ability to understand what any of it meant. She lost that conceptualization. She had the functional part down, but not the conceptual part, and that was lost to her forever. Think how tragic that would be. I want you to have the whole picture, the conceptual part as well as the procedural part. So let's do some examples. I want to find the derivative of the function f of x equals x cubed plus, let's say, 5x. So, in our solution, the first thing we'll write is f prime of x equals. After the equal sign, the very first thing will be the limit as h goes to 0. Now, do you remember the definition of the derivative? It was f of x plus h minus f of x all over h. By the way, guess what the first question on the next exam will be? State the definition of the derivative. You have to know this. You've already inscribed this on your brains. Make sure you get all of the parts, including the limit. On the next line, I'm going to begin with equals because I'm asserting equality with what is above. I'm not doing anything actively with the limit yet. I need to work with the function evaluation. So what is f of x plus h? That's going to be x plus h cubed plus 5 times x plus h. Everywhere you see an x, you replace it by x plus h minus f of x. Well, f of x is x cubed plus 5x. And don't leave off these parentheses here. If you do, you'll be violating the order of operations agreement. The minus will only apply to the first term, not to both. Divided by h. Now, how do I carry out a perfect cube like this? I need to FOIL that out. Do you remember Pascal's triangle? There's the 0 level, which begins with just a 1. The 1 level has a 1 and a 1. Each new row begins with 1 and ends with 1. In every row succeeding, the 2 row will begin with 1, will add the 2 above, and will end with 1. So in the 3 row, we'll begin with 1, we'll have a 3, and then a 1. The 4 row will have a 1, 4, 6, 4, and then 1. Why is this so important? Think about it. If I have a plus b to the power 0, I get 1. A plus b to the power 1 is a plus b. Notice the coefficients are 1 and 1. A plus b squared is a squared plus 2ab plus b squared. The coefficients are 1, 2, and 1. Guess what you get for a plus b cubed? You get a cubed plus 3a squared b plus 3ab squared plus b cubed. 1, 3, 3, and 1. Note that the powers on a are decreasing by 1 in every term, whereas the powers on b are increasing by 1 on each term. So you can calculate the power of a plus b to any number, any natural number, using Pascal's triangle. It follows then that we have the limit as h goes to 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed plus 5x plus 5h minus x cubed minus 5x all over h. Whew. So, what cancels? Clearly, x cubed cancels with x cubed, and I'm labeling those as the first thing that canceled. 5x cancels with 5x. Now, is there a common factor on every term that remains? It looks like there's a common factor of h on every single term that is left over. We'll factor that h out. We'll have 3x squared plus 3x times h, we'll have 1h left over here, plus h squared, taking an h out from here, and then plus 5 all over h. The h in the denominator canceled. This is a good sign. Taking the limit as h goes to 0, two of these terms are going to disappear. We'll be left with 3x squared plus 5. So let me state what we've just shown. We've shown that if f of x is x cubed plus 5x, then f prime of x is 3x squared plus 5. What does this f prime of x represent? It's a sort of slope function. You input the x, it outputs the slope of the tangent line at that x. Here's a typical sort of problem. Find the equation for the tangent line to the function f of x equals x cubed plus 5x at x equals, let's say, 1. In this case, we already know f prime of x is 3x squared plus 5. The slope that we seek is going to be f prime at 1. That will give us the slope of the tangent line at x equals 1. That's 3 times 1 squared plus 5, or 8. But it takes more than just a slope to write down the equation of the line. We need the point slope form of a line. That's y minus y naught equals m times x minus x naught, where the point x naught y naught is assumed to be a point on the line. We need a point. So far, we only have the x-coordinate of a point. To calculate the y-coordinate, we'll plug that number 1 into the function. We get 1 cubed plus 5, which is 6. So we're dealing with the point 1, 6, and the slope 8. It follows that the equation of the line is y minus 6 equals 8 times the quantity x minus 1. We can simplify and solve for y if we wish. There are certain functions I just want you to know the derivative of. One example would be f of x equals the square root of x. Yes, I want you to be able to calculate it in several different ways eventually, but I also want you to just remember the answer that we get from the following computation. F prime of x is the limit as h goes to 0. We have to evaluate the function at x plus h. That's going to be the derivative. That's going to be the square root of x plus h minus the square root of x all over h. At this point, we need to do that classic computation. We need to rationalize the numerator by multiplying both numerator and denominator by the conjugate of the numerator. The conjugate is what you get when you replace the sign with the alternate sign. Minus gets replaced by plus. We'll do that on both top and bottom because we don't want to change the value of the expression. We only want to change its form. When we FOIL out this numerator, we'll have root x plus h times root x plus h, which is x plus h. We'll have root x plus h times root x and a minus root x times root x plus h. Those two terms cancel. We're left with only the lasts multiplied together, and that gives us minus x. This is over h times, and don't distribute the h. The h and the denominator must cancel. The square root of x plus h plus the square root of x. These x's cancel. After the x's in the numerator cancel, we're left with only this term h. It will cancel, leaving a 1 in the numerator. In the limit now, as h goes to 0, we will have 1 divided by, if h is going to 0, we'll have root x plus root x. That's 2 root x. I want you to remember forever that the derivative of the square root of x is 1 over 2 root x. You're going to commit this to memory and keep that in memory forever. There's another one I just want you to know. Let's look at the function f of x equals 1 over x. Then f prime of x is the limit as h goes to 0. Remember, we evaluate the function at x plus h. That's 1 over x plus h minus the function f of x, and that'll be 1 over x all over h. You can see that if you just plug in h equals 0 now, you'll end up with 0 divided by 0. And that just means more work. The thing that you need to note in the numerator is that we are subtracting fractions. How do you subtract fractions? The answer is clearly, you have to have a common denominator. So I need to multiply the first fraction by x over x. The factor of x has to go in both numerator and denominator, or else I'm changing the value. On the second term, I need to multiply by x plus h over x plus h. I'll have the limit as h goes to 0. In the denominator here we have h. If I write that as h over 1, when you divide a fraction by a fraction, you invert and multiply. I'll have 1 over h times. What's left over is x times x plus h. Removing this for now. We'll have x minus h. That leaves minus h since the x's cancel. We can now cancel the common factor of h in numerator and denominator, and then take the limit as h goes to 0. We'll get -1 over x squared. This gives us the fundamental formula. The derivative of 1 over x is -1 over x squared. This formula you're just going to remember. We use these formulas so often, you have to just store them in memory. There's another variant of the definition for the derivative that you need to be aware of. It's based upon this idea. Suppose you have some function f of x, and you want to find the slope of the tangent line at a. You'll move over to some point x. The gap instead of h now is x minus a. And so the derivative at a will be the limit. The difference in the y values will be f of x minus f of a, whereas the difference in the x values will be x minus a. And we'll have to take the limit as x tends to a. We'll need to use this formula pretty soon. It turns out the existence of the limit in the definition of the derivative implies a certain level of smoothness on the curve. In particular, it implies that there does exist a well-defined tangent line on the curve. That's not true for all functions. If I have f of x equals the absolute value of x, what is the tangent line at x equals 0? You can see that this function isn't quite smooth enough to have a well-defined tangent line. You can balance tangent lines all over the place here, and so it doesn't have a derivative at x equals 0. It will have a derivative everywhere else, but just not at x equals 0. Also, if a function is not continuous at some point, there is no well-defined tangent line that you can put there, and so the derivative won't exist at such points. We have the following theorem, though. If f is differentiable, meaning the limit of the derivative actually exists at x equals a, then f is continuous at x equals a. Notice this theorem is in the form statement A implies statement B, where statement A is f is differentiable and statement B is f is continuous. So differentiability implies continuity. The converse of this statement, B implies A, would be the converse. The converse of this statement is false. You can have continuous functions that are not differentiable, and the absolute value is a perfect example. Remember the definition of continuity? There were three parts. The limit exists, the function value is defined, and the limit equals the function value. Here's what we'll do. We'll take the limit as x goes to a of f of x minus f of a. You can see then that we're assuming the function is defined at a, and if in the limit as x goes to a, we can prove that this limit is equal to 0, then the limit of f as x tends to a will equal f of a. Our goal is to prove that this limit equals 0. On the very next line, we'll put something into this difference. We're going to express it kind of like a derivative, but to pay for that, we have to put another factor of x minus a to the side. You can see then that we've assumed differentiability, which means that this first factor must tend to f prime at a as x tends to a. That limit must exist. We've assumed differentiability. But also, as x tends to a, the second factor goes to 0. And that means the limit is 0. Therefore, the limit of f of x as x tends to a is equal to f of a, and f is continuous at x equals a, and the proof is done. Differentiability implies continuity, but continuity does not imply differentiability. Let me give you another example. Suppose A is the statement, I am in Paris, and B is the statement, I am in France. A implies B would be the statement, if I am in Paris, then I am in France. Let's suppose that's a true theorem. Let's look at the converse. B implies A. If I am in France, then I am in Paris. Well, that's not true. That's a false theorem. So an implication can be true, and yet its converse false. You need to understand that. First, I want you to consider what happens if a function is constant. What happens if the function outputs a constant k for all x? Then, what is the slope of the tangent line? Aren't all of the tangent lines horizontal? And don't horizontal lines have slopes equal to 0? But you can see this immediately. This will be the limit as h goes to 0 of, if I plug x plus h in, I get k out. And if I plug x in, I get k out. This is the limit as h goes to 0 of 0 divided by h. As long as h is going to 0, we're assuming that h is not equal to 0, but only nearby. For all such ratios, in the limit as h goes to 0, we're just taking a bunch of ratios that are equal to 0. And hence, the limit is 0. Just as you anticipated, the slope of the tangent line at each point will have a slope, will be 0. You can see then that the derivative of any constant is 0. We'll call that a theorem. And we've just proved it. Now, I want to go through a sequence of examples. This follows a pattern in mathematical theory called exploration, conjecture, and proof. We're going to explore what happens to certain power functions when we calculate the derivative. We'll arrive at a conjecture, and then we'll have to prove it. Suppose my function is f of x equals x. Everything is exactly a pass-through. Whatever you plug in, that's what you get out. This is the line y equals x. The slope of the tangent line at each point is obviously 1. The derivative then will be the limit as h goes to 0. This function evaluated at x plus h is x plus h. When I subtract f of x, I'm just subtracting x. And then dividing by h. You can see that the x's cancel, and then I'll have h over h, which is 1. Evaluating the limit, I get 1, just as you might anticipate. But I want you to think about this as x to the power of 0, maybe even 1 times x to the power of 0. In our next example, we'll look at f of x equals x squared. What is the derivative now? It is of course, the limit as h goes to 0. F of x plus h will be x plus h quantity squared minus f of x, which is x squared, over h. That equals the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. Don't forget the middle term. The x squareds cancel out. We're left with two terms in the numerator, each of which has a common factor of h. We'll write this as the limit as h goes to 0 of h times 2x plus h divided by h. You can see that h's cancel. That's good news. Now, taking the limit as h goes to 0 of what's left over, we get 2x. It follows then that the derivative of x squared is 2x to the power 1. Do you see what I'm getting at? Let's try this one more time. Suppose f of x equals x cubed. F prime of x will be the limit as h goes to 0. Don't forget my limit. X plus h cubed minus x cubed over h. We need to FOIL out this perfect cube. We can use Pascal's triangle for that. So the next line begins with equals the limit as h goes to 0. I'm trying to teach you good habits about how to continue writing these expressions on separate lines. X cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. The x cubes get canceled, and each term that's left over in the numerator has a common factor of h. We can take one factor of h from each and cancel it with the factor of h in the denominator. Now, when we take the limit of what's left over with respect to h as h tends to 0, these other terms will go to 0 and will be left with 3x squared. This gives us the derivative formula. The derivative of x cubed is 3x squared. Can you make the conjecture now? Our conjecture is really a theorem called the power rule for derivatives. Or sometimes just the power rule. The theorem is that if you take the derivative of x to the power n, you get nx to the power n minus 1. You bring the power down and then subtract 1 from the exponent. You're going to need to remember this forever. For what values of n does this theorem hold? It doesn't have to be constrained to only whole numbers or natural numbers, or even integers. We can use any real number here. For instance, if n is equal to pi, you'll get pi times x to the power pi minus 1. So any real number will work for the power rule for derivatives. The proof uses the binomial theorem. Do you remember the binomial theorem? The binomial theorem was the basis for Pascal's triangle. It says x plus y to the power n is equal to x to the n plus n choose 1, x to the n minus 1 y, plus n choose 2, x to the n minus 2 y squared, plus dot dot dot, plus n choose n minus 1, x y to the n minus 1, plus n choose n, which is 1, y to the n. These binomial coefficients are the entries in the various rows of Pascal's triangle. They always begin with 1 and end with 1. So we're going to calculate the derivative of the function f of x equals x to the n. By the definition, that's the limit as h goes to 0 of x plus h to the n minus x to the n divided by h. I have to be honest with you. This proof is defective. The binomial theorem only works if the exponent n is a whole number. So this proof will work as long as n is a whole number, but it will not work if n is an arbitrary real number. We'll have to patch that defect later when we've developed more theory. However, using the binomial theorem for now, at least we'll have the proof for whole numbers. We'll have x to the n plus n choose 1 x to the n minus 1 h plus all the way down to h to the n minus x to the n all over h. The x to the n's cancel. On every term that remains, we have a common factor of h that can be factored out. We'll have the limit as h goes to 0. And what is n choose 1? N choose k is n factorial over k factorial n minus k factorial, according to the binomial theorem. N choose 1 will be n factorial over 1 factorial n minus 1 factorial. 1 factorial is 1. N factorial is n times n minus 1 times 3 times 2 times 1. N minus 1 factorial is n minus 1 times 3 times 2 times 1. Almost everything cancels except for the n. So n choose 1 is n. I'll factor an h out. On the next term, we have n choose 2, x to the n minus 2. We had an h squared here. We'll now have just an h. And we'll end with h to the n minus 1, since we're taking one factor of h from every single term. The h in the numerator and denominator cancels. We're left with this expression, which in the limit as h goes to 0, all the terms except for the first one cancel out, and we get n times x to the power n minus 1. That's a temporary halt to the proof. At least we know the proof is true when n is a whole number. We'll have to work a little harder later on to prove the power rule when n is an arbitrary real number, but we will do that. I want to show you how the power rule is related to some facts I've already asked you to memorize. Suppose I'm taking the derivative of the square root of x. The way to do that using the power rule is to first convert the radical into a rational exponent of 1/2. Now, by the power rule, we get 1/2 x to the 1/2 minus 1. That's 1/2 x to the negative 1/2. A negative exponent means shove it across the division symbol. We'll shove it across the division symbol and make the exponent positive, changing its sign. We now have x to the 1/2 in the denominator, and that is the square root of x. So the derivative of the square root of x is 1 over 2 root x, just as I asked you to memorize. I know that it's always possible to reproduce this last calculation. Instead of memorizing it, you can derive it from the power rule every time. But I want you to have it at your fingertips a little faster than that. There's an advantage to using memory over processing. when you're writing a computer program and it's executing a computation millions of times, instead of running the algorithm over and over again, sometimes it's better to store results in memory. For instance, suppose I have to calculate something where I multiply two numbers together. Instead of multiplying them together millions of times, why don't I multiply them together once and store that in memory? It's a lot faster to recall that value from memory than it is to perform the computation again and again and again. Sometimes those computational efficiencies in programming can lead to very important results. There's the famous example of the program that was written for controlling the space shuttle nozzles. It was badly programmed and it was pointing the nozzles a little too slowly, and the space shuttle wasn't going as efficiently as it should. Once the algorithm was corrected, the nozzles were responding more quickly and the space shuttle could be guided more accurately. So you can see, using memory is really important sometimes, instead of processing power. Now I know a lot of you think, well, you just go through the reasoning process again. No. You need to memorize certain things in order to increase your computational efficiency in the future, and that's what we're aiming at. I also want to look at the example of the function 1 over x, which I'll rewrite as x to the power minus 1. When you shove it across the division symbol, you change the sign of the exponent. In this case, the derivative then is negative 1 x to the negative 1 minus 1, or negative x to the minus 2. To get a positive exponent for our answer, we'll shove the x squared over the division symbol and get negative 1 over x squared, verifying again that the derivative of 1 over x is negative 1 over x squared. I've asked you to memorize that. Please do. We can now calculate some derivatives that you couldn't calculate before. What about the cube root of x? We should rewrite that as x to the power of 1/3. Roots can always be converted into rational exponents. It follows then that the derivative is 1/3 x to the negative 2/3. To get a positive exponent, we'll shove that across the division symbol. The 3 in the denominator of the exponent is a cube root, where the 2 in the numerator is just a square. So we can rewrite this as 3 cube root of x squared. In the next theorem, we prove that the derivative has 2 algebraic properties. These are called linearity properties, and demonstrate that the derivative is something called a linear transformation. First, when you take the derivative of 2 functions added together, you can take the derivatives of each term separately. Second, if you take the derivative of a constant times a function, this constant factor can come out of the derivative process and be multiplied onto that function. These 2 properties will be enormously useful. So we'll prove them. Let's prove these. I'm going to write it to save a little bit of room here as f of x plus g of x quantity prime. That is, of course, the limit as h goes to 0 of f of x plus h plus g of x plus h minus f of x plus g of x all over h. we can use the commutative and associative laws of addition to rewrite this sum as f of x plus h minus f of x over h plus g of x plus h minus g of x over h. Now, provided the limits on both terms exist, from our limit theorems we know we can distribute the limit and do two separate limits. The limit as h goes to 0 of the difference quotient f of x plus h minus f of x over h, and the limit as h goes to 0 of g of x plus h minus g of x over h. But that's simply f prime of x plus g prime of x. For the second property, we have that constant factor k, which can be factored out of the difference quotient and out of the limit. Constant factors can be factored out of limits, according to our limit theorems, which gives you that part of the proof as well. So we'll declare the proof of the theorem over. The power of this last theorem is that it gives us, in conjunction with the power rule for derivatives, the ability to calculate the derivative of any polynomial. So example, let's take the derivative of 5x squared plus 3x plus 7. According to the theorem, that's 5 times the derivative of x squared plus 3 times the derivative of x plus the derivative of 7. You can take the derivative of each term separately, and constant factors can be brought out of the derivative process. So you can see that we get 5 times 2x plus 3 times 1 plus 0. And the answer is 10x plus 3. In the future, we won't write these intermediate steps. We can see from here that the 2 gets brought down and multiplies onto the 5, giving us 10. We'll subtract 1 from the exponent, so it's just x. The derivative of x with respect to x is 1, so the second term has a derivative equal to 3. And then, of course, the derivative of a constant is 0. I want you to be careful about the notation that you use, in particular, the order of operations agreement. PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. This is the order in which you do operations from left to right. Suppose, for example, that I have y equals 2 divided by 3x cubed. How do I calculate the derivative? I need to push the x cubed into the numerator, rewriting the function y as 2/3 times x to the power negative 3. At this point, I can calculate y prime by bringing the power down and subtracting 1 from the exponent. This gives me y prime is negative 2 over x to the 4th. What if I did the following, though? 2 over 3x quantity cubed. It's different now. You can see that I'll have 2 over 27x cubed, which I'll write as 2/27 x to the minus 3. It is at this point that I can calculate y prime most easily. The negative 3 comes down. It will cancel with the 27. 3 goes into 27 9 times. We'll have negative 2/9 x to the negative 4, or negative 2 over 9. x to the fourth. You can see the answers are not the same because we had a different order of operations. We're trying to increase the class of functions that we can take the derivative of. So far, we can calculate the derivative of any polynomial. In fact, as long as we're dealing with terms, separate terms, that have a constant times x to some power, and that power is a real number, we can calculate the derivative. What about sine of x? We need to be careful here. In this notation, what we really mean is the sine of x, because sine is a function. It's not a factor. It's not multiplied onto x. It's a monster eating that x and doing terrible things to it. I want to calculate this derivative, but I need to recall to your memory two limit facts. First, in the limit as x goes to 0, sine x over x, you get 1. In the limit as x goes to 0, 1 minus cosine x over x, you get 0. We'll need to use these two facts. So if I'm calculating the derivative of sine x, that is by definition the limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. Now, we have the sine of the sum of two angles. Do you remember the sum of angle identity for sine? The sine of a plus b is the sine of a cosine of b plus the sine of b cosine of a. A lot of students reach this point and don't remember the sum of angle identity for sine, but from now on, I want you to remember this. We're going to need this at other points throughout calculus. But for now, this is the moment for which you memorized the sum of angle identity for sine. This is the time where you get to use it. It's the sine of x times the cosine of h plus the sine of h times the cosine of x minus the sine of x all over h. We need to recombine things a little bit. I'm going to take this first term and combine it with this last term. They have a common factor of sine of x. I'm going to factor that out. And what's left is cosine of h minus 1 over h. In the term that remains, we have a cosine of x, and then sine of h over h. Now we get to use those two limits that I asked you to remember from before. This last limit, as h goes to 0, gives you 1, and this limit gives you 0. So the derivative of the sine function is cosine. I want you to remember this formula forever too. The derivative of sine is cosine. Let's see if that makes sense. The sine function looks like this. The cosine function looks like this. Let's think about the slopes of the tangent line for the sine function. At x equals 0, the sine function takes off out of the origin at an angle of 45 degrees, a slope of 1. cosine function has a value of 1 at x equals 0. It gives you the slope of the tangent line at x equals 0. One cycle is repeated in 2 pi units. One bump ends at pi. The peak of that bump is at pi over 2. The slope of the tangent line there at pi over 2 is 0. The cosine function completes the period in 2 pi units halfway across at pi. And at pi over 2, it goes through the x-axis having a value of 0. The value of the cosine function at pi over 2 is the slope of the tangent line to the sine function at pi over 2. It has to be. We've just proved it. Okay, let's calculate the derivative of cosine x then. This should be the limit as h goes to 0 of the cosine of x plus h minus the cosine of x all over h. Do you remember the sum of angle identity for cosine? Yeah. The cosine of a plus b is the cosine of a times the cosine of b minus, you always get the opposite sign here, the sine of a times the sine of b. So for us, that's the limit as h goes to 0 of the cosine of x times the cosine of h minus the sine of x times the sine of h minus cosine of x all over h. Again, we need to collect the first and last terms here. We'll take the limit as h goes to 0, cosine of x times cosine of h minus 1 over h minus sine of x times the sine of h over h. This first term has a factor that tends to 0, and the second term has a factor that tends to 1. We see then that the answer is minus sine of x. So we have the derivative of cosine x is minus sine x. Let's see if that makes sense. The graph of cosine goes like this. The derivative at 0 will be 0. When you move forward towards pi over 2, the derivatives go negative. They go negative. And they reach a maximum negative derivative of minus 1 at pi over 2. The derivatives go back to 0 by the time you get to pi. After pi, the derivatives go positive, reaching a maximum at 3 pi over 2. Of 1, and then down to 0 again at 2 pi. You can see that this is kind of an upside down sine graph. It's been multiplied by negative 1. The derivative of cosine is minus sine of x. We've just seen that the derivative of sine x is cosine x. And the derivative of cosine x is minus sine x. I'm asking you to memorize these two facts. Take the time and do that right now. For example, suppose my function is something like 5x squared plus 2 cosine of x. Of according to the rules of differentiation that you know right now, this should be 10x minus 2 sine x for the derivative. There's one more function I want to show you the derivative of today, but I can't prove it. We're going to have to give you mere plausibility arguments for this derivative. The proof will have to come when you're in Calculus 2. We give this to you in Calculus 1, and that's the reason why your textbook is titled Early Transcendentals. The number e we've seen is a transcendental number. The function that we're going to talk about is the function e to the power of x. We want to calculate the derivative of this exponential function with the so-called natural base. The only thing that we have to go on right now is not the power rule. This is not a power function. Power functions are of the form x to the power of a constant. This is a constant to the power of an x. That's a different animal altogether. The only thing we have to go on is the definition of the derivative. So we'll take the limit as h goes to 0, e to the power x plus h, minus e to the power of x, all over h. Now remember this, if I have a to the power of b plus c, that's a to the power of b times a to the power of c. So we have the limit as h goes to 0, e to the x times e to the h minus e to the x all over h. The numerator of the difference quotient has two terms. Each term has a common factor of e to the x. E to the x can be factored out not only of the numerator, but also out of the limit, because it doesn't depend upon h. So we have e to the power of x times the limit as h goes to 0, and what's left is e to the h minus 1 over h. Now, this is the point from which things get a little sketchy. I want to calculate this limit as h goes to 0 of e to the h minus 1 over h. You can see that if I just plug h equals 0 in, e to the 0 is 1, 1 minus 1 is 0, 0 divided by 0 in the context of limits means more work. So, what is that extra work? The only thing that we can do right now is evaluate the function at points h that are close to 0. Let's try 0.1. My calculator gives me 1.05170918. 1/10 is not very close to 0. We need to squeeze in much closer to 0, maybe 0.001. Let's try that. My calculator gives me 1.0005000167. The first number was close to 1. The second number is even closer to 1. What do you hypothesize as the limit? We're going to take it as a given fact, something that we will prove in Calculus 2, that the limit as h goes to 0 of e to the h minus 1 over h is 1. It follows then that in our derivative calculation for e to the x, since this factor is 1, we get e to the x. We have then that the derivative of e to the x is e to the x. I want you to memorize that and know it forever as well. e to the x is interesting because it's a function having derivative equal to itself. Is this the only one? Not quite. It's also true that if I have any constant times e to the x, constant factors can pull out of the derivative process. And the derivative of e to the x is e to the x. So I get that constant times e to the x. So any constant times e to the x has derivative equal to itself. The existence uniqueness theory from differential equations will imply that these are the only functions that have derivatives equal to themselves. We, of course, introduce the derivative of e to the x before we can fully justify it, because some students who take calculus only take calculus 1, but they still need to know the derivative of e to the x. We can't fully justify that now. We will fully justify it in calculus 2. As another example, suppose I have the function, say, x to the 7th plus sine x. F prime is 7x to the 6th plus cosine x. Suppose I have the function, let's say, cosine x plus e to the x. Then f prime of x is minus sine of x plus e to the x.